Thank you very much for the invitation. So today I want to speak about a specific model which arose in the interest of physicists quite some years ago, so within the last 10 years, and that's the quantum random energy model. But in addition to this, I also want to give you somehow the bigger perspective on why looking at this model might be interesting in a quest for understanding more about the topic which we've heard from David Hughes, namely the question, how do eigenfunctions of general many particle systems behave? Okay, so the talk is partitioned in three sections. So I will start off with this particular model, namely the quantum random energy model, and describe a theorem about how the low energy regime of the spectrum of this model looks like, and with a particular focus on something interesting happening there, namely a phase transition of the ground state. And then in the third part of the talk, which is the more somehow outlook part, I will go to the question of resonant delocalization, a phenomenon which one might expect also in this kind of model, and give some advertisement for some talks to come. Okay, let me start off with the quantum random energy model. So what is this model? Well, think about somehow the following graph, namely the Hamming cube. If you're a physicist, you could imagine this graph as the configuration space of n spins taking values plus or minus 1. So it's a graph with 2 to the n number of vertices, where each vertex has exactly n neighbors, okay, because you could flip any of the n spins in your entry. Now, the operator which I'm interested in is composed of two parts. First part is the Laplacian on the Hamming cube, which again, somehow, if you're more physics interested, you could think of this Laplacian actually as acting as a transversal magnetic field on your spins. So the Laplacian just has a term which is a constant, n, and it's in fact nothing else but the sum over all n spins of the x component of the Pauli spin matrices acting on those n spinor halves. So this Laplacian is, of course, well studied, and one can write down the full spectrum. The eigenvalues are just given by the even integers, as it turns out. And the normalized eigenfunctions you can also write down. Now, just for future reference, let me draw a picture of how the spectrum of the Laplacian looks like. So you start off with a ground state. The ground state corresponds to an eigenvector which, so to say, is totally extended. And it's at zero energy. And then starting from that, you take the even integers up to the highest excited state, which would be 2n, which is, so to say, the antipode of that. And, well, n might or might not be an eigenvalue, depending on whether n was even. Now, so you have these two n eigenvalues, but your Hilbert space is 2 to the n. That means that you have quite some considerable amount of degeneracy in your system. So the question is, what are the which degeneracies are in these eigenvalues? And the degeneracies are just given by the binomial coefficients corresponding to the subsets by which you can label the eigenvalues. So in other words, of course, the ground state is non-degenerate. It's a single ground state. This is already n-fold degenerate, and the degeneracy sort of piles up in the center of the band. And the highest excited state is, again, a non-degenerate state. Now, what we're interested in is a perturbation of this Laplacian by a random multiplication operator. So in other words, what we're studying really is a random Schroedinger operator on this particular graph. So for future reference, I've also introduced sort of a coupling constant here, so a non-negative number. And U is my potential. So you can think of this potential, if you go back to the spin language, of being an operator, which is just a linear combination of the Z components of your spins. Okay, so the only quantum effects which we have in this system are buried in this Laplacian, which represents this transversal magnetic field. Now, in order to see something interesting at all, of course, you should put the Laplacian and the perturbation on equal footing. So what we'll be interested in is perturbations by potentials, which are again order n, because order n, as we just saw, was the range of the spectrum of the Laplacian. Now, in this talk, just for being specific, I want to mainly talk about what happens if the potential is actually, in fact, a Gaussian random potential. So in each of these vertices, you install somehow an IID, standard Gaussian random variable. And in order to satisfy my requirement that the fluctuations live on order n, I have to scale up things by square root of n. Okay, so that the minima and maxima of this, again,
G
order n.
means the sum of somehow Gaussian.
No, G of sigma is just one random Gaussian distributed random variable. Sigma labels a vertex in that graph. Okay, so it's really just think of.
Why is it of order square root of n unless there's a sum somewhere?
No, because there are so many. There are many, 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 many. I'm just asking. See, I have 2 to the n.
G is some function of the sigmas. What function
No, no,
of the sigmas?
no. G itself is a random variable. So think about your old Anderson model.
Right.
Okay. So on each of those, so it's just that I'm just not interested in ZD. I'm interested in a more crazy graph. Okay. And on each of the vertices, I'm attaching a single Gaussian random variable.
There is just something with the normalization, because you say the infinity norm of U is all n, and then you put me square root of n there, because there the size would be square root of n, no?
The typical one is square root of
The
n.
typical one is square root of n, but the extremas are on range n. Yes, because I have 2 to the n random variables. The typical size of the fluctuation are indeed square root of n. But the extremal size of the fluctuation is, in fact, order n.
So what you called it a random variable, but really a random field.
It's a random field.
That's what confused me.
Okay.
It's not a single
Yes.
number. It's one.
It's
a function.
It's a
and because of fluctuations, that function.
That function-
Value square root of n. That's what it is.
yes, it's typical square root of n, but the extrema live somehow on order n.
I'm being very veneering.
Sorry to confuse you. Z. Oh, it's the Z component. So for those of you who come from physics, that's just the Z component of the of the Pauli matrix. So you can, if you're a physicist, you can think of this as a spin system, in which, well, your spins are subject to a transversal magnetic field, and you have some energy landscape, which is, you can think of sort of being made as of a function of the Pauli spin, of the Z components of the Pauli spin matrices, which create U. Okay? Of course, I can't, it's not one of your favorite XXZ models or any of that. It's just sort of a helping for physicists, really. Okay, so that's the model which I want to talk about. Now, why could one be interested at all in this model? Well, so these kinds of models actually arise in various different contexts. Context of the last 10 years, exactly this model made some splash in the community of quantum information people, where Fari, Goldstein, Gutmann, and Snipser proposed so-called adiabatic quantum computing. And that's the question that you have some complex energy landscape. Think of your function U, and you are asked find the minimum for a typical realization. Now, how do you do this in an efficient way? Here is Fari's proposal. You can do it in an adiabatic way using quantum mechanics. Namely, the idea is that you evolve, so you think about somehow the question in a quantum mechanical way, namely you want to find the minimum of the Hamiltonian U. Okay, now as a quantum mechanics person, you know how to do this, where you just start off with a Hamiltonian whose ground state you know. So, for example, take the Laplacian. That ground state we know, I exactly wrote it down. And then adiabatically transform this ground state to the ground state which you don't know. Okay? So evolve your system with this kind of Hamiltonian, switching between the known ground state and the unknown ground state. And then if you open a book on quantum mechanics, then what people will tell you is sort of, yes? Well, this is what I want to come to, okay? So if you open a book on quantum mechanics, what people will tell you is that, okay, so how long, what's the required time in order to make this computationally effective? Well, the required time is just inverse proportional to the square of the minimal gap in your family of Hamiltonians. That's the rough idea. So see, I mean here, so at s equal to 0, the gap size was order 1. It would be wonderful if through this whole process the gap size would actually stay of order 1, right? However, if the gap size somehow closes exponentially in n, then there's no algorithm which can compute this there's no quantum mechanical algorithm which can compute this ground state in a time which is faster than exponential in n.
Can I just say something?
Yes.
I was impressed in that paper that in fact the potential was not a fully random
No,
potential.
it's not a fully random
It was
potential.
something quite different.
Yes, it's a,
It has nothing to do with a random potential.
yes,
Because
right.
it was a sum of which makes
It's-
analysis quite a bit.
No, it's a right. It's so people have okay. So in this paper, I can say more about this paper. In this paper, actually, what they looked at is they looked at permutations of a given landscape, and they have actually quite a general theorem which says that even if you're not thinking about sort of starting off with the Laplacian, that this quantum adiabatic optimization proposal always fails. Now, that's not the original paper, but a later paper. But so this, to answer your question, this is not effective. It's not an effective proposal, and it's known that you cannot beat the Grover time.
So they were basically claiming sub-exponential.
They were, yes.
And that could very much depend on the potential.
Yes, it could very much depend on the potential, but they have a very general scheme which tells you that for all kinds of systems, this will fail. In particular, it will also fail for the random system. Okay, so I'm not claiming that I'm actually contributing really with that part of research to their community, because they.
I don't know if anybody ever even checked, say, if it would have a fully random potential, say, if you would have, say, if you take me now estimate,
Yes.
what it would really give you. So I would imagine it could give you just an exponential lower bound, and not a sub-exponential.
Yes.
But something like a minam, you could never play with the kind of potential they are using there.
That's true, yes, yes, right. But they have other ways of arguing why this proposal is actually not so good as they thought in their first paper.
So but actually,
Okay.
Binami is not, this is not just Binami, you are changing the parameter S, and there are level crossing driven by that. So
But you could still somehow with,
Only depends on the potential, and will give you certain separation.
right, but
Yes.
here there's another phenomenon, you have level crossing, and then the gap is even smaller than Binami would give.
yes. Let me okay, so let me say somehow there's a set of questions which you could be interested in the question of the gap size, but as it turns out, there are actually more effective ways of answering the question whether this is an effective algorithm. And with that kind of research, I'm not really claiming that I'm making sort of a big impact on their field. Okay, it's just sort of as an appetizer that this is in the background of these questions. Okay, because
For a Gaussian field, finding the minimum, there must be very effective probabilistic methods.
yes, yes,
Right? So
probably
this
with
seems
the
crazy to
simulating
bring in
annealing.
quantum mechanics
Yes,
to
yes, but they
solve
didn't.
that problem.
Right.
If you
No.
had a more complicated you,
Yes.
maybe it would be different. But
Yes.
it seems crazy if
To
the
do yes,
model you're looking at.
yes, correct. I totally agree. Yes, sure. Okay. Good.
I could probably even do a calculus.
Okay, so let me mention sort of as a second set of people who've been looking at these sort of problems is people around which are sort of closer to me, maybe people who work in disordered quantum systems from the physics side. And in particular, Altschule has been proposing such kind of mean field models for studying the localization transition in disordered n-particle systems. Now, okay, so one could argue how much, if one understands these mean field models, one understands about a real disordered many-particle system, but at least somehow that's a valid, yes. Yes. Now, these type of models also show up in actually mathematical biology of all fields, where it was Eigner and Schuster who proposed random landscapes as the fitness landscapes and studied, in fact, the semi-group, not the quantum mechanical time evolution for this type of problem. Okay, so much just for the motivation why you could be interested in these kind of questions. Now, I want to, in my first part of the talk, I want to focus on the low energy spectrum, and the low energy spectrum is actually something physicists looked at numerically in this model. In fact, exactly in this quantum random energy model, it was studied by Jörg, Schaller, Kurchen, and Max, and also by some people in Italy. And what people find there, unfortunately, they used a different normalization, so let me translate this figure down to the present parameter choice. They find a transition in the ground state at a coupling constant, which is exactly given by 1 over square root of 2 log 2, where for kappa, for the coupling being smaller than this critical coupling constant, the ground state energy is non-random, it doesn't fluctuate, and it's given by the old ground state energy, which was 0, and a kappa squared correction. And if you look above the critical value of the coupling strength, then the low energy states are concentrated on the lowest values of your potential landscape, and their energies, in fact, are given just by the potential up to a very huge constant, which is equal to n. Okay, and what somehow, if you think about somehow this quantum adiabatic proposal, which also drove the interest of these people here, is exactly at criticality. What you will see here is that you change the ground state, you change the behavior of a ground state from an extended ground state at low kappa, which would be here, to a localized ground state at large kappa, which would be that regime. And there's an almost crossing. It's avoided on a scale which is exponential in n. Okay, so we have a closing, an exponentially closing of the gap size there. And what I want to do in this, in the first part of the talk, is to just explain how some of these features come about. Okay. Now, let me do first some heuristics in order to get you started how to think about these systems. We've already figured out that you have this random potential landscape U. You can ask about where is the minimum, where that's very known. You have 2 to the n Gaussian random variables. You scale them by square root of n, and the minimum is in fact exactly somehow sitting at order n with a coefficient which is 1 over the critical coupling constant with fluctuations on top of that. In fact, I mean, all the extreme values, as you know, somehow form a Poisson process about this energy with an exponentially increasing intensity. Okay, so this is the process which you see just switching off the Laplacian to purely looking at the properties of the Gaussian random potential. Now, again, if you're sort of a naive physicist, and that's what they did in their papers, you might say, okay, so if you're at large coupling constant, you know somehow what is the big gangster in your Hamiltonian, namely the potential. So let me start with perturbation theory and ask what happens to those localized states when I turn on the Laplacian. And the Laplacian just sandwiched in those perturbed states just gives a constant, namely this n. Okay, so to first order perturbation theory, you led to the belief that your energy eigenvalues are just given by n plus whatever the potential values were. Now, if you, on the other hand, sort of start from the delocalized phase where your random landscape is the perturbation, you start from one of those eigenstates of the Laplacian, for example, this totally extended state which forms the ground state, and you ask, how much is it changed by the potential? Well, to first order perturbation theory, it's, well, I neglected here the Laplacian term, which we know is 0 for the ground state. It's just an average over the potential, where that guy doesn't fluctuate because of the central limit effect. So it's something which is small on the order of 2 to the n over 2. Okay, but this is exactly somehow what one can then also prove. So let me first go to the last part of the story. So let us now suppose that your coupling constant is small. Okay? So what you expect when your coupling constant is small is that these localized states, they...
Small means it's independent of n when you say small.
Yes, yes. Because, see, the coupling constant was already rescaled by square root of n, so the n is already put sort of in the potential. Okay, so what happens here is that the localized states, well, they can form at most energies which, well, reach from n down to n times 1 minus kappa divided by kappa c. Because I've explained to you the minimum of the potential lives on that order of magnitude. Okay? So that's somehow the threshold for the localized states. Now, if kappa is smaller than kappa c, then your low energy spectrum will not contain localized states, but it will just be perturbations of the delocalized states. Okay, and that is what is proven somehow in the first theorem. In case kappa is smaller than kappa c, then I can describe, if you give me some security distance epsilon, so somehow away from where at all the localized states can reach, I can describe to you the full low energy spectrum of this Hamiltonian. And the full low energy spectrum of this Hamiltonian is in fact given, as we've just calculated in this naive perturbation theory, by a renormalized version of the eigenvalues of the Laplacian, and the renormalization is given by minus kappa squared. And they don't fluctuate because I can pinpoint them up to events which are exponentially small within bars of size roughly 1 over square root of n. Okay, and I know exactly somehow how many eigenvalues you would find in those balls, namely they match up to the degeneracy which was present before, which would be this n choose little n. Okay? Okay, moreover, in fact, their eigenfunctions will still be delocalized, namely the L infinity norm, which for the ground state without the perturbation squared would be just 1 over 2 to the n, because it's a uniformly extended state, would get a certain renormalization, which is given, in fact, by the famous entropy function, okay, which I called here gamma of x. Just to remind you, gamma of x somehow it's a function which roughly looks like that. So it has its maximum at ln2, where x is equal to 1.
I'm a little
Half.
bit confused there because, say, if you drop the potential, you will have, so looking at your eigenstates, you have high multiplicities there, right? Basically, it's the multiplicity of the binomial coefficients.
Yes.
So these guys are not necessarily flat.
No, they're not necessarily flat. Yes.
So they have basically their
Yes.
infinity bound is a binomial, the square of it is a binomial coefficient.
Yes, which you will see somehow if you go to higher energies, because that is taken care of by this entropy function.
Basically
Right.
You're saying that degeneracy is just not lifted.
And I'm saying somehow the degeneracy is not lifted. It's lifted to somehow order 1 over square root of n.
The gaps are of order 1, and then
Yes.
square root of n.
You see, in this regime, somehow nothing fluctuates. It fluctuates only on scales which are presumably much, much smaller than that, but I can control it up to a scale 1 over square root of n. And then up to this scale, of course, I mean, this is 2, right? So this distance here is still 2. So these balls here are overblown. They're circles of radius 1 over square root of n. Yes?
It may be useful to notice that within each of these blocks you have a random matrix statistics.
Yes.
So that it's all compressed to a tiny scale.
Right.
Smaller than
So what will happen, so here we had these n eigenvalues. Of course, the degeneracy will be lifted. But as you can see somehow from this stupid computation down here, the lifting of the degeneracy probably occurs on an exponential scale. And okay, if you're actually, we have somehow the world experts on random matrix theory, so here's a challenge. What you will see, presumably, if you magnify now this spot here, you will see eigenvalues which cluster now on this exponential scale, and they will form somehow random matrix statistics. Okay? But that's not proven in this theorem. So what's proven in this theorem is sort of a much cruder information. What's the heuristic for this? Well, I think the heuristic is part of what the proof here is. And so bear with me for a second. You can ask this question later if it's not clear. Okay, so but that is what's proven. Now, it always seems a bit sort of
What would you explain
daring.
about the statistics of those eigenvalues?
Random matrix,
But what kind? GOE?
GOE, because it's where I'm starting off with a real ensemble.
I shouldn't see Poisson.
No, nothing. No Poisson. We'll see Poisson in a regime later.
And does this literally mean kappa less than kappa c or just kappa small?
No, it means literally sort of kappa less than kappa c. I don't need any smallness of kappa. It's not in this sense a pure perturbative result. Let me actually tell you sort of how it's proven. In fact, the proof is not complicated. Now, so the first thing which you might wonder about is sort of what this statement sounds very complicated, but that's actually a very easy statement. That's just due to the hypercontractivity of the Laplacian on this graph. So, so to say, what happens here is that you can control the semigroup, and the semigroup is just, if you control it in the absolutely brutal way, just pulling out the minimum value of the potential. Probably I got a sign here wrong. Then you're just left with computing somehow the semigroup of the Laplacian, and this has these strong hypercontractivity properties, and that is the result. No? Okay, so this is not a big miracle. Now let me come somehow to the description of the eigenvalues and why we can pinpoint them to the circles which I've told you about. Now, let me now sort of do the following. Let me project to the center of the band of the Laplacian. So take the band center n and a bit of epsilon nearby. And remember, that is actually the regime where most of the levels of the Laplacian live. Okay? Because of the huge degeneracy, that is where your binomial coefficient piles up. Now, I will not be interested in the center of the band, but for low energies, I'd be rather interested in the complement of the center of the band. This projection I will call P epsilon. And later on, I will take epsilon to be varying with n, namely somewhat exactly on the scale of 1 over square root of n. Now, as I just emphasized, and let me do this again, most of the states don't live in the subspace P epsilon. In fact, the dimension of P epsilon divided by the dimension of the Hilbert space is exponentially small in n. That's very okay. So now here's somehow the lemma which actually which gives you these corrections. It's a basic concentration of measure statement. Namely, the basic realization is that if you just project, and that goes to the core of your observation why you expect random matrix statistics, if you just project the potential onto the band, onto everything aside from the center of the band, then these matrices are in fact small on the exponential scale, because we've seen that the dimension of P of epsilon divided by 2 to the n is in fact an exponentially small number. Remember, this is e to the minus epsilon squared n divided by 2. Okay, so on average, the norm of this random matrix is exponentially small, and on top of that, it doesn't fluctuate. The fluctuations are also somehow on the exponentially small scale. Now, how can that be? Well, the fact that it doesn't fluctuate is really somehow just the standard concentration of measure statement. The norm is convex, and it's in fact a Lipschitz continuous functions of the basic random. Yes?
I was wandering off a little bit. I just realized that I missed the definition of P epsilon.
Excuse me. Okay. So P epsilon. So this is, so if you just take the Laplacian, you just project on the subspace of the center of the band, that I call Q epsilon, and the rest is called Q epsilon. Okay? So, and what I mean by somehow center of the band, I give myself a freedom of room epsilon n. Okay. Good. So this is in fact just the standard concentration of measure statement, that the norm as a function of the basic random variables is Lipschitz continuous, and the Lipschitz constant is in fact given by in terms of the dimension of this projection relative to the total dimension of Hilbert space, which I chose to be exponentially small. That's why the fluctuations are on this exponentially small scale. Now, what you have to sort of go through is you have to calculate an upper bound on the average of the norm of this random matrix, and that's just done by a standard moment estimate. So instead of calculating the average of the norm of the random matrix, I just calculate a high Schotten power and expand and use basically the fact that I know many things about the kernel of this projection, because I know it explicitly.
In fact, you have even a more precise estimate, which is true in general, which is basically a pure factor of n. It's the square root of the ratio between the dimension of the range of P epsilon and 2 to the n.
Oh, I see.
Which will correspond in this range with what you write here.
I see.
You can actually make a
More
very precise estimate of that.
okay. I should.
Standard entropy considerations.
Okay. Okay.
Say at infinity versus L2.
I see. Okay.
Gives you basically the same result.
So maybe I work too hard out of ignorance. Okay, I would be, yeah, okay, good. Now, how do you put everything together? Well, it's the good old friend, the Schur complement formula. Where's Jeff? So in order to study the eigenvalues, I just study the resolvent on this subspace, and by just the standard Schur complement formula, this is what it boils down. Now, this part you know very well, because I've just told you somehow how PUP looks like. That's a random matrix which fluctuates on this exponentially small scale. And that is responsible somehow for the level broadening of each of those little eigenvalues, where in fact I would expect this random matrix statistics. And they're coupled through the rest of the system in the standard way. Now, how does one glue this together? Well, the basic realization is that, see, with the help of this method, this is nothing which actually is particularly tied to the fact that this is a Gaussian, U is a Gaussian random potential. This was actually far more general. And this also allows me to, of course, make statements about matrices of the form PU squared P. PU squared P is again a random matrix which I can plug in the previous lemma. And in fact, it's a random matrix which is centered about, well, n, right? Because the standard deviation of the Gaussian was 1. And it doesn't fluctuate on that scale. So the deviation from it being n I can control. So in this way, I can, for example, control everything if I would just erase the middle part. Now, why can I control Q epsilon H Q epsilon? Well, in Q epsilon H Q epsilon, that is in fact very far away from the energy which I'm looking at. Because remember, this is now just the Laplacian, which is basically where all the tails are chopped off, which is basically a constant, namely n. Okay, and I'm subtracting from this constant somehow the random potential, which anyway can only reach to this size. Okay, good. And if you glue things together, you can see with these methods that, in fact, the remainder term in the Schur complement formula is more or less this constant up to an error which you can control, and that gives you the kappa squared correction. Now, this also gives you the intuition why I expect that I see random matrix on the finer scale, right? Because it should be true that a good approximation to what I see on the finer scale are these matrices PUP. And they will be random matrices in the standard sense with a funny correlation structure.
But you know the correlation structure quite precisely?
Yes, yes. I know it precisely, and I think it fits into what Laszlo is working with his PhD student. Okay, good. Now, oops, I'm running a bit out of time. So, okay, so this tells you sort of what happens if kappa is actually smaller than the critical coupling constant in the low energy regime, which is dominated by the Laplacian. Then you could wonder somehow, what about the rest of the cases when kappa is now large? And can I also control somehow what's going around here? And in fact, if I'm not so far away from the tip of where the random potential can yield to, I also know somehow how I can describe these localized states. And let me just run through this, just the idea and not how the proof actually works. Where you have a very good intuition where those states which at all arise at the tip of the potential are created. They are created in the large deviation, negative deviation sides of the potential. And if you choose somehow delta small enough, then what you will see is somehow these teeth in which these localized states can form. They will be well separated, very much at the tip of where the random potential can reach. And in order to somehow calculate or describe how they look like, you can just form balls about those tips of a. Now, this is just a cartoon of how the hypercube configuration space looks like. And I'm looking actually at balls on the hypercube, and this would be sort of essential. So I'm looking at balls on the hypercube of radius gamma, where gamma times n, where gamma is small. And yes, just the regular distance on the hypercube. And to an exponentially, up to an exponential error in n, I can actually describe all those states by the states in the direct sum of what you see in the large negative deviation sites in those balls, and what you see somehow on the rest of the system. Now, let me tell you somehow why you should be content with that, because first of all, the spectrum of what you see in the rest of the system looks much what we've seen in the previous theorem, namely consists somehow of a random system in which you just remove the teeth of the potential, right? So you are basically operating with a random potential which has effectively a smaller kappa, okay, because you just remove the teeth. It's a regular random potential. And on the balls, you can just exactly calculate the spectrum of these Dirichlet Hamiltonians. This is sort of an exercise, and you know, in fact, that the miracle on the hypercube is that if you Dirichlet restrict to a ball of radius gamma times n, then the shift of the ground state energy is in fact substantial. It is substantial in the sense that the ground state of the Dirichlet Laplacian on this ball gamma times n is shifted up by n times, well, this number here. Where gamma is small, it's basically shifted up by n. Okay, so this is helping you, because on all those balls, the Dirichlet ground state of just the Laplacian is now sitting here and not where you're operating with your energy. Okay, and then, well, if you somehow assume that the only thing which is going on your ball is just a large negative deviation and something regular on the sides, then you can employ rank 1 perturbation theory to calculate where the ground state of this perturbed operator on this ball is exactly located. And it's exactly located by n plus kappa times where the potential value on the center is up to a renormalization, which is given by the safe energy of the Laplacian. Okay. Moreover, if you look at the normalized ground state, so the ground state eigenfunction, this decays exponentially. So even if you sum over the rim of the ball, you get an exponentially small error. And that is the part which wants to couple somehow to the rest of the system, right? So it couples somehow with an exponentially small signal to the rest of the system. And that helps you somehow getting this direct sum decomposition, at least for low energies. Okay, now I won't get into the details of this. I promised you to do some third part of the talk, in which I now want to go away from the low energy spectrum and ask the question, what do we actually expect for higher energies? Okay, so suppose we're in a situation where kappa is larger than kappa c, so your potential can reach up to here. I can very well describe the energy structure which is sitting down there. But the question is, how do the typical eigenstates somewhere there look like? What would we expect? Okay. Now, here is a proposal. So what we expect here is, in fact, something which we've seen, a phenomenon which we've seen on the tree, and which we also see in a toy system, which is the phenomenon of resonant delocalization. As you well know, random operators may form extended states by just joining local quasimodes. We cannot prove this in many situations, but that's, if you ask the physicists, that's a common sort of paradigma. And the corresponding eigenstates may or may not satisfy what you've heard from David Hughes, this eigenfunction thermalization hypothesis, which is sort of a heuristic version of the equidistribution principle. And what we want to do is, in fact, clarify conditions for when resonance takes place and put forward the idea that this eigenfunction thermalization hypothesis might actually be violated in many systems. Okay? Now, so far we can only sort of come up with examples which possibly violate this eigenfunction thermalization hypothesis, and I believe that the quantum random energy model will be one of them. Now, let me talk about an example which I think I've talked about many times so far, but just for those of you who haven't seen that, well, if you go away from sort of these effective mean field many particle systems and go to an infinite graph, namely what physicists call the beta lattice or the regular tree with a fixed coordination number, and just study the standard Anderson model, namely Laplacian plus random potential, you can think of this random potential again in terms of a Gaussian random field. So this is, of course, now not a random matrix, but an operator on L2. And you can again ask about how do the eigenfunctions typically look like. Well, here's the phase diagram. Now, the surprising thing which we found in a work which we did 2 years ago with Michael Eisenman was the following, that there are actually extended states appearing not only in a perturbative regime of where the spectrum of the Laplacian lies, which for lambda equal to 0 is that little interval going to 2 square root of k, k as being the branching number. But there will be extended states appearing actually in the L1 spectrum of the Laplacian. Now, these extended states will presumably actually not be uniformly extended, but they will rather want to live in locations. Think about somehow how they are created. They can at all, in a Gaussian random field, live there because you for a small lambda, you created a large negative deviation to accommodate a state at this energy, because the Laplacian can't help you here. Okay, so so you have these large negative deviations in which these states are created, and the only mechanism by which they can be extended is that they resonate. But they won't be uniformly extended. In particular, if you go to a nearby energy, somehow what you will see is that the state somehow lives somewhere completely different, okay, which would clearly violate your eigenfunction thermalization hypothesis, which you talked about 2 weeks ago. Now, on top of that,
Is this an artifact of the infinite surface?
yes,
In this model, is this just an artifact of the fact that the number of sites is growing exponentially?
yes, and I wouldn't call this an artifact, it's a feature. It's a it's a feature because in any sort of many particle system, if you look at how the configuration space looks like, it will also somehow have if you carve out a volume, you will have exponential volume growth. So that's why I call this a feature.
So do you think the entire region of extended states has that property?
No, no. Let me be okay. Let me be sort of okay. So what we proved is sort of a statement about the nature of the spectrum, in the sense that we proved the existence of absolutely continuous spectrum down here. To be honest, we somehow didn't resolve the question, how do the eigenstates really look like? Now, there are people physicists who've now taken up this work in Paris, who've asked the question, what kind of level statistics do we see? Now, for them numerically, of course, the level statistics looking at these regions is not something which is approachable, because the density of states is exponentially small here. So when they look on a computer, they don't see anything. But what they see is they go to zero energy and they sample a window up here and they decrease the perturbation. And what they see is when they come from the localized regime, that there's a critical value which you kind of expect where the AC states appear, which is known, at least for large values of kappa. And then within the extended states regime, they claim that they can see Poisson statistics there. And then only later there's a second phase transition to GOE statistics, which would support the idea that these eigenfunctions, in fact, they live somewhere. They are not uniformly extended, which is always a mechanism to create somehow GOE level statistics. Yes?
I'm sorry, what did you say? Valuation statistics when you get to the first critical.
Okay, so this is the spectral phase diagram. Here one can prove pure point spectrum, here one can prove AC spectrum. What these people here claim is that there's a second phase transition. If you ask where does it flip from Poisson, which we know is up here, to GOE, which presumably happens down here, it is not at that critical value of lambda, but rather at a smaller critical value of lambda. That is what these people put forward as an idea, and numerically somehow studied, supported.
Is that for
that is
these tree-like structures?
Yes, no, it's exactly for the beta lattice, where there's a question.
If I start to take a sparse graph and
So exactly, somehow one has to,
regular graph.
yeah. So what they do is somehow they of course don't look really at a finite tree, where we have proved that you will see anyway always Poisson statistic irrespectively of where you are in the phase diagram. But what they look at is these random regular graphs. They do look at the random regular graphs and study the phase transition there. And they claim these two critical values, they don't match. Okay, so and this would sort of support the idea that there is a regime of extended states which fails this eigenfunction thermalization hypothesis. Okay, now I think I only have 6 minutes. So one can sort of put a bit of mathematical definitions behind this formulation of what resonating quasimodes means. In particular, you can associate to a given quasimodes their tunneling amplitude. So if these quasimodes somehow form, for example, a two-dimensional subspace, whose projection I'm calling PJK, a smart way to define a tunneling amplitude would be again through a sort of Schur complement formula, and calling just the off-diagonal matrix element the tunneling amplitude of the quasimode J with a quasimode K.
Could you explain what you mean by
Quasimode?
So like an
Yes, it's an approximate eigenfunction. Yes. So by a quasi. So I call a quasimode a pair, of an energy and a wave function for a Hamiltonian if it satisfies an equation of the following form, and then there's the notion of discrepancy which comes with a quasimode. Okay, so that would be the quasimode EJ psi j with discrepancy DJ, and DJ is somehow the quality, some form of quality of the quasimode. So that's at least somehow a standard definition, which seems a standard for the community of those quantum chaos people. I'm not sure. I think, to my knowledge, it was first put to use by Colin de Verdier.
Here are you making an orthonormal set of quasimodes?
Yes, for simplicity, let me talk about an orthonormal set of quasimodes.
Of course, this criterion, it doesn't have to be a localized quasimode.
No.
But here you're making localized?
No, it doesn't have to be localized, but somehow in the, okay, so in, okay.
The interest is in
In the interest, somehow, if you're interested in would there be localization versus would these localized states, which you think, which you have a heuristics about what they should be, would they melt? Right, like in the situation on the tree. I mean, I know somehow how these states are created. They're created in these large negative deviation sites. And then I can ask, would they melt? Would they somehow form a larger delocalized state? And as a physicist, somehow, I guess, what you would look into is you would study the typical gap size for these quasimodes, something like 1 over the number of those guys times their density of states. And you would compare this number at this energy to the tunneling amplitude. Okay, now, in fact, what I want to advertise, and that's something which I think Michael Eisenman will talk about in 2 weeks, and I will talk about in 1 week, probably in Banff more, is that this yes, this condition is actually quite effective. So, oops. Okay. Now, there's a system which is more approachable than the quantum random energy model, but which shares some of its features. It's just the Laplacian plus random potential on the complete graph. Now, the Laplacian on a complete graph actually is just up to an energy, a constant energy, a rank 1 projection, namely the rank 1 projection on the totally extended states. So think about the complete graph over m sites. Here is a cartoon, and do the same thing, somehow study Laplacian plus random potential, and now put the random potential on the scale of the Laplacian, which clearly here is order 1, and the m dependence, which you need to introduce in the coupling constant, is again somehow related to square root of 2 log 2, if you think about this as m being 2 to the n times 1 over the square root of n. So it's really the same normalization of what we've seen before. So if you think about m as being 2 to the n, it's really sort of a toy model, a one-band model for what the QRAM looks like. Now the quasimodes are the localized modes here. Okay, and their gap size, the inverse gap size is indeed related to the density of states times the total number, well, times this coupling constant, because I put a coupling constant in front of it. Rho here is just the standard Gaussian. So rho of v is e to the minus v squared over 2 divided by square root of 2 pi. Okay, and you can go through this dogma and calculate what the tunneling amplitude is, because everything is explicit here. Now the tunneling amplitude, if you go through this calculation, turns out to be m times the gap size times the Hilbert transform of the rho, plus a term which is of course fluctuating, because you can convince yourself it's fluctuating on order 1. Okay? Now, what this dogma would tell you is that you need this ratio to be smaller than 1. And if you can satisfy this for some energies, then you expect resonant delocalization there. So you expect that these quasimodes, which we have here, in fact form an extended state. And lo and behold, you can go through the analysis of what the Hilbert transform looks like, and you find that at energies near 0 and energy near -1, at least in this case, if the coupling constant is larger than square root of 2, you indeed find delocalization. Okay, so that's the theorem which we can prove, is that indeed if this is of order 1, then we can describe first the rescaled eigenvalue point process in a complete way. It goes to something which we dubbed the Bogomolny-Galland-Schmidt process, which I don't want to describe here, so I beg you to wait for the talk of Michael or my talk next week. But the important thing for our purposes and for the discussion which I put forward is that these eigenfunctions around this energy which satisfies this condition is in fact delocalized. Now, it's delocalized in an L1 sense. So if you compare somehow the L1 norm versus the L infinity norm, then this guy diverges in the energy window. However, they are still localized if you look at them from the point of view of L2, where the L2 mass actually lives. The L2 mass is still concentrated on order 1, where the L infinity mass lives. So it is delocalized in this sense, but still localized in this sense, which means that it's not a uniformly delocalized state. Indeed, somehow again, to drive this point home, these guys, they would not satisfy your eigenfunction thermalization hypotheses, but they occur. Okay, I think I went already sort of a bit over time. And for those of you who will be in Banff, I will explain that in more detail. And for those of you who are not in Banff, we'll hopefully see this, a bit more of this story in 2 weeks. Okay, so what is the conclusion? Well, the conclusion is the following, that in this QRAM model, I gave you a complete description of the low energy spectrum, somehow basically in accordance to what physicists predict, that there is this ground state phase transition at the critical coupling constant with an exponentially closing gap. And the second take-home message is that there's a conjecture which is worthwhile looking into for various model systems, which is this resonant delocalization conjecture, where you're asked to compare the typical gap size of the quasimodes in your system to their tunneling amplitudes, which has the potential of actually creating eigenfunctions in these systems which violate what is known as eigenfunction thermalization hypothesis or quantum ergodicity. And this is also, if you go through the calculation, something which you expect not for the renormalized versions of the eigenfunctions of the Laplacian, but what occurs in the center, or what occurs sort of in the gaps of those guys, where eigenfunctions will settle in.
What about in Q sub E?
Q sub E?
What the states look like in there?
Probably extended. Now Q sub E somehow looks a bit like, whoops, Q sub E looks a bit like this guy at 0 energy, like the complete graph at 0 energy. Let me remind you somehow, for the complete graph, the energy spectrum, if you in this new normalization, so everybody sits at 0 for the Laplacian,
Right.
aside from one guy, which I put at -1.
So this result over here is for states near -1.
No, it's for states which are near here and near here, blown up on the relevant
Also
scale.
near 0.
Yes, yes. Right.
And you think that'll be true near 0 energy up here?
Presumably, yes. Presumably, somehow they will create extended states. It will be also near 0 there.
Well, of course, these are sort of, in some sense, extended, in some sense, not. Right? These guys.
Yes.
And you
Are you
think
asking me somehow if I expect
do you
the
think something like that
eigenfunction
happens up there?
thermalization hypothesis is satisfied here?
So
This I don't.
that's a rigorous statement that they are delocalized, or it's just a conjecture?
No. I mean, the only rigorous statement which I have to offer is the low energy spectrum of the QRAM,
Right, okay.
and what happens in this toy model. Okay, everything else is now you take that and now you come up with conjectures what could actually happen there. Yes.
Okay, in fact, just comment that this model seems to be considered in physical literature
Yes,
years ago by Alexander Osipov.
Osipov, yes.
And he claimed that what called compensation ratio, I think sum of psi to 4 was
Yes.
finite. So like
Yes.
is it in agreement with that?
Yes, it's in total. Yes, it's in total agreement with this.
Okay.
So but the thing is, you should not only, I mean, the participation ratio, which is just one measure of localization. And if you look at somehow the L1 property of the eigenfunction, then you will find that these look actually as delocalized. If you look at these, I mean, this immediately implies something about the inverse participation ratio. This is only for, no, this is for all s smaller than 2.
Oh, so you think the transition is at p?
Or just a second, let me see, smaller than, I'll tell you somehow how these things look like. Okay, so if you ask somehow how does the wave function look like, well, it will somewhere there will be sort of the maximum of the wave function, okay, and then you can ask somehow how does the fall off. So there will be the next guy, and the next guy, and the next guy, and so on.
In this model, there's no distance.
Right, exactly, right. But I can sort of rank order them by who's the fattest guy, who's the next fattest guy, and so on. And if you ask me somehow what kind of function is this, well, this will be sort of a 1/n fall off, which will lead you, if you look at L2, to believe that it's localized. But of course, if you look at it at L1, it's delocalized.
So that's the marginal case.
Yes. So
So 1/n, the dividing line
is 1.
At 1.
It's 1, yes, it's 1.
At 3/2, you'd also have.
Yes, at 3/2 I will also have it, yes, but at s smaller than 1, I won't have it.
But of course, the probability is given by 2.
Hmm?
So 2 is the probabilities. So it's a probability distribution for the states. It's localized.
Yes, yes.
So in terms of physics, it's 1. In terms of
No. No, this is only one aspect of the physics, right? Somehow, I mean, it's not that. No.
No, I think it's useful to mention these two physical criteria. One is geographic localization, the other is recurrence. So if you ask what's the probability of transit to the state to be back again,
Then it's this. Yes.
On the other hand, if you ask sample twice from the state, what would be the characteristic distance between the locations of where you would find yourself? Then, as soon as here the geography is such that any two states are as far apart as possible. So this weak delocalization actually means that geographically it's as far delocalized. The geographic spread of the wave function is tremendous, as big as it gets.
But that's because distance 1 is the maximal distance which you can make.